I'm Duncan O'Dell from McMaster University, and it gives me great pleasure to introduce Monika Schleier-Smith. So you think, so ICAP's a big deal, give a talk, but I heard you give a talk on Mindscape, on Sean Carroll's Mindscape. Does anyone else listen to that, or is it just me? I think he's amazing, that guy. Anyway, great. No further ado, Monika, please.
Thank you so much. So the title of my talk today is Atoms Interlinked by Light, Programming Interactions and Probing Entanglement. And I thought to sort of motivate the role of the light, I would start with just a quick reminder of what it is that many of us in this crowd today love about cold atoms as a toolbox for quantum science. Right? These are systems where we have extraordinary control down to the single particle level, detection capability, scalability, and those ingredients are opening a range of applications from extraordinarily precise measurements, such as clocks, to many-body simulation, to ultimately perhaps quantum computation. Now, one additional ingredient that's really essential, particularly for these latter applications, is control over interactions. And I've shown a couple of pictures here of some of the beautiful physics that arises, for example, from contact interactions in lattices or van der Waals interactions between Rydberg atoms. One limitation that I want to point out about sort of this toolbox I've shown so far has to do with kind of the connectivity of the interactions in these systems. So typically interactions decay with distance. Atoms interact most strongly with their neighbors. Why do I say that's a limitation? Well, that governs the physics that we can access in these systems. Just to give a few examples, if I have, let's say, some lattice with nearest neighbor interactions between some qubits, that naturally gives rise to something known as a cluster state. That's a resource for computation. If I had actually the same type of interaction, but every atom were talking to every other one, that is a natural way of generating something known as a squeeze state. That's a resource for enhancing precision measurements. If I add some randomness to these interactions, that could actually be a way of taking some quantum information that's initially locally encoded in one qubit and very rapidly allowing it to become hidden in complex correlations and entanglement in a process that might actually be a model for what happens to information that falls into a black hole. And if I have a high degree of programmability of interactions in the quantum system I build in the lab, then I might be able to take some real-world problem, like some optimization problem, and map it to minimizing the energy of this well-controlled quantum system. So we would love to actually have the opportunity to have more versatile control over the graph of interactions in these cold atom systems that we build in the lab. And the approach that we take in our group is to actually use light to mediate interactions among atoms. So we trap atoms within an optical resonator that allows, in principle, any atom to talk to any other in a way that's mediated by a single mode of light. And some things we've been working towards over the past couple of years are enhancing the programmability of the graph of these interactions and also combining the non-local connectivity afforded by this cavity with local detection to be able to probe spatial correlations and entanglement in the system. So before we get to sort of these new ingredients, let me just kind of give you a simple picture for how I can think about these photon-mediated interactions. So in the simplest case, if I had two atoms, two-level atoms, and I wanted to engineer, let's say, a spin exchange interaction, I could do that by allowing one atom to flip its spin, emit a photon into the cavity, and let that photon be absorbed by another atom, right? And that will give me some flip-flop process mediated by the light. In the experiments I'll talk about today, there won't be just two, there'll actually be many atoms, and these platforms of many atoms coupled to a single mode of light already actually have a very strong track record in, for example, generating entanglement in a massively parallel fashion, particularly for applications in quantum metrology that I think you'll hear about, for example, in the next talk. And these are systems where, provably thousands of particles are entangled in fairly simple, conceptually simple quantum states that one can sort of visualize by, like in this picture, here's some picture showing essentially the collective magnetization of some group of atoms and the fluctuations around that. So this is powerful for these metrological applications. For other directions, such as quantum simulations, one wants to sort of venture beyond this space of states that can be described by a single collective spin. And this is also a direction that's widely explored in the community is exploring applications to quantum simulations, where one relies on incorporating motional degrees of freedom or additional cavity modes in order to sort of access richer many-body physics. Now, one thing that's kind of common to almost everything, all of the examples I've put on this slide, is that typically one probes these systems via collective observables. For example, the light leaking out of the cavity can be a powerful way of probing the system. But there's a new direction that's pursued in my and a few other groups, where we're augmenting that with also starting to do real space imaging to directly observe and image the dynamics inside the cavity. So the experimental platform we work with looks like this. So it's really just 2 mirrors, sort of 5 centimeters apart. And between those mirrors, we have a standing wave of light that essentially pins the motion of the atom. So the motional degree of freedom will be frozen out, and the dynamics is within the spins. And in the experiments I'll show today, we operate with actually an array of atomic ensembles within the cavity. So up to about 20 of them. This is this sort of a millimeter-long array. And we typically work with some thousands of atoms per ensemble, which has some benefit in giving us a collective enhancement of the atom-light interaction strength in the system. To make the atoms interact, I kind of gave a cartoon picture before, but a little bit more explicitly, we actually want to have interactions we can control with light. And so we send in a control field that drives a Raman process in which we flip a spin and put a photon into the cavity. That process is off-resonant, but there's a resonant process where another atom absorbs that photon and flips its spin. And I'll add sort of one more ingredient in the experiments I show today. So we work with rubidium atoms, which have a spin-1 ground state. And so a way that we actually typically probe this system is to initiate all atoms in the 0 state of this spin-1 system. When we send in light, that can mediate a process where 2 0 atoms turn into a +1 and a -1 atom. And in general, there's no reason one or the other of these atoms should be in the +1 or the -1 state. And so that looks like it might be a mechanism for generating entanglement. And that actually is something that is well studied in Bose-Einstein condensates, where direct collisional interactions between atoms give rise to this type of spin mixing, these correlated atom pairs. And that has been demonstrated as a resource in those systems for generating highly entangled states. In our system, what does it look like when we sort of turn on the light and watch these dynamics? So here's, again, our array of in this case, 18 clouds of atoms, with all of them initially in the 0 state. And this is basically 30 repetitions of the same experiment where we turn on the light and after some time measure the populations in these 3 internal states. And you'll see that there's sometimes kind of more population in the -1 state, which is always correlated with more population in the +1 state. This is kind of the first signature of this generation of this spin mixing dynamics where we generate correlated atom pairs in the +1 and -1 states in the cavity. So one thing that you'll also observe, though, here is if you look at the spatial structure, this is a millimeter-long array of atoms, but there's no interesting sort of spatial structure. The correlations extend across the entire cloud. And that's because we have a single mode of light that's mediating the interactions in the system. So if we'd like to start getting more control over the graph of interactions, we need to sort of add an additional ingredient. Ideally, we might want sort of arbitrary control of the coupling graph, but we'll be a little more modest and ask, can we start to control, for example, the dependence of interactions on distance? And so there's a nice trick for doing that that involves adding a magnetic field gradient across the system. And the first thing that happens if we add a magnetic field gradient across the system is it introduces an energy penalty for forming these +1, -1 pairs if the atoms involved are any distance apart, if they're not in the same site of the array. But this process is still allowed on a given site, and so if one measures, for example, correlations between the number of atoms in state +1 on site I and the number of atoms in state -1 on site J, you'll see that these correlations are strong on the diagonal, meaning we've kept this on-site interaction but turned off the long-range part of the interaction. And the nice thing about this, though, is that actually we can now controllably reintroduce interactions at a distance of our choice by turning on essentially a second frequency in our control field. So the idea is now we can have processes where an atom absorbs a photon of one frequency and emits a photon of another frequency in a way that bridges the energy cost of creating these pairs at some distance. And that allows us, by choosing the modulation frequency of our laser field, to choose the distance at which the interactions are on in the system. And so this is just showing sort of correlations as a function of distance and as a function of our modulation frequency, and you'll see that this nicely tracks. So the great thing about this is literally this is just modulating the intensity of the light. So that's easy to do, and it's easy to do with any waveform of our choice. And so that means that we can actually, by controlling the modulation waveform, have even more flexible control of the structure of interactions in our system. One simple example of this is if rather than having this sort of simple sinusoidal modulation, I additionally pulse this waveform on and off at a higher frequency, I can choose that frequency to essentially take what would be a one-dimensional chain and connect the ends of it. This is actually a very general trick, this sort of additional pulsing, for taking whatever graph of interactions I have here and turning it into the same graph with periodic boundary conditions. So that kind of starts to illustrate that one can have in the lab some interaction graph whose geometry doesn't need to be the same as the physical geometry of the sites in my array. And so with that general principle in mind, we can now sort of play games with applying different modulation waveforms to our system and generate a whole range of different interaction graphs. So we could have this ring, nearest neighbor interactions and periodic boundary conditions, but we can also add additional frequency components to make, let's say, a Mobius strip, or a cylinder without the twist, or this ladder-like geometry, just by changing the waveform shown here in purple that we apply with the light. Okay, so actually these illustrations here are some kind of a reconstruction of the kind of some effective geometry of our system directly based on the measured correlations. So points that are close together indicate sites that are interacting strongly and hence strongly correlated when we measure spin correlations in the system. And if you want to know more about exactly what goes into reconstructing these pictures, I'll refer you to a poster on Wednesday by Avakar Parawal. Okay, but one thing I'll mention right away about these graphs is that, so essentially the color of the bonds indicates something about the sign of the correlations between sites. Are they ferromagnetic or anti-ferromagnetic? And that actually matches also the sign of the coupling that we've programmed in. So how do we control the sign? That actually just has to do with a pi phase flip of the modulation at a frequency that turns on interactions at a certain distance. So that's something we can control. But it's not actually immediately obvious. It might not be obvious to you why, if I turn on, let's say, anti-ferromagnetic interactions, I should see anti-ferromagnetic correlations. And the reason is I haven't actually done anything like adiabatically prepared a ground state of this system. All we've done is suddenly turn on the light and measure the correlations. So if that seems surprising, I can give you actually, I'll tell you one more thing that sort of explains why this is possible. Why is it that what we prepare looks sort of like a low energy state of the XY model on this interaction graph? So the reason is actually that, to sort of add one more detail about this spin-1 system, in our system we have some linear Zeeman shift, but also a quadratic Zeeman shift. That means that if I just had non-interacting atoms, the energy of two m equals 0 atoms would actually be slightly lower than the energy of a +1 - 1 pair. So there's a cost in internal state energy to this process of generating these pairs in the + and -1 states. To compensate, the atoms as we generate these pairs can actually lower their interaction energy. And so these dynamics actually sort of naturally give rise to spin textures that essentially look like kind of low temperature states of a classical XY model. So just as an example, when we engineer, I showed on the previous slide, this sort of triangular ladder with anti-ferromagnetic interactions. So this is kind of an example of frustration where ideally you'd have oppositely aligned spins on neighboring bonds. The best they can do in this case is to align themselves at roughly 120-degree angles. And if we measure the correlations in the system, it's in fact consistent with that sort of 120-degree ordering. So this is kind of neat that actually just the dynamics of this pair creation are giving rise to something that look like low temperature states. It's potentially interesting for applications in optimization, and actually on these graphs that I can that are translation invariant and that I can sort of plot in some 2D picture, it's not a hard problem to find the ground state of the XY model, but generically if one has other graphs with non-local couplings, if one were to add disorder and make richer structures of interactions, this actually is classically a hard problem to find these ground states, and it would be wonderful to explore sort of these quantum dynamics offer some advantage. So that's a direction we would love to investigate this in this system. I can't promise there's a quantum speedup. Actually, if you want to read some theory we've been doing about another system where one really would expect a quantum speedup, I'll refer you to this paper here. But here, this would be nice to explore experimentally. So, the type of graph one would want to build is one where there's not a simple low-dimensional representation where I can draw you a picture of the geometry in 2D or 3D. And that's something we have been exploring in a different context, motivated by rather the direction of quantum simulations. And in particular, we've been motivated by the question of whether we can build in the lab some kind of toy models exploring ideas from quantum gravity. And so if you listen to the Mindscape podcast, maybe you heard a bit about this. But so, this might sound sort of like a obscure direction. So let me just give a little bit of kind of background on sort of what is this idea of sort of exploring quantum gravity. And I want to introduce this on a bit of a philosophical note. So actually, here's a philosopher who we should all be grateful for. This is Democritus, who invented the concept of the atom. And there's this wonderful quote from him where he says that sweet and bitter, hot and cold, color, all of these things are by convention. And in truth, there are but atoms and the void. Okay. So what does he mean by that? To sort of put this in modern language, you could say that what he's saying is that sort of macroscopic behaviors such as taste, temperature, color, really emerge from the microscopic configurations of individual atoms. And at the time, that was something revolutionary because atoms were not something that we could just see under the microscope. Okay, so today we know that the fundamental building blocks of matter are atoms. But what about the void? So there are still some open questions about what about space-time? Is it really smooth? Or is this also some kind of an emergent phenomenon where there's really a more fundamental underlying description that we just haven't yet seen? So here's an example. So could curved space and gravity also emerge from some discrete constituents? So here's an example where I've shown you, this is actually a picture by Escher showing a tiling of a hyperbolic space. You can tell it's curved because you should think of all the fish as being the same size, but there are many, many more fish around the circumference than across the diameter, and that tells us there's actually negative curvature here. Okay, so as physicists, we don't think that the discrete constituents are fish, but what you might imagine is that sort of the underlying theory is one where actually the ingredients are some quantum degrees of freedom, maybe qubits that are these blue dots sort of around the circumference. And that the notion of curved space and gravity actually is a manifestation of correlations between those qubits. And so the white lines here are supposed to indicate something about the structure of entanglement in the system. So this concept that curved space and gravity might emerge as a description of entanglement is known as holographic duality. Holographic because there's sort of one additional dimension that emerges from describing the structure of quantum correlations compared to the physical system that lives on the boundary. Okay, so we were curious, could we build some toy model in the lab where you can sort of start to see this notion of an emergent geometry? Here's the toy model, actually, that we built. It involves some interaction graph where interactions are on at distances that are powers of 2. It's something rather exotic that you wouldn't just find in nature, but we can program that in. We can control whether the strongest interactions are the nearest neighbor ones or the furthest neighbor interactions. So let's build this model. And so as before, we can sort of turn on the interactions, measure some spin correlations, and then we're going to try to ask what is sort of a natural geometric representation of this physical system. And the first thing we can do is kind of as before, we can ask where are the correlations strongest between which sites, and find kind of the best fit embedding of these sites, in this case in 2 dimensions, so that ones that are strongly correlated are situated near each other. And now the question is kind of, suppose there's something like this bulk geometry I showed before that represents the structure of the correlations. How could we see that? Well, one thing we can do is start asking which sites are most strongly correlated. We just measure spin correlations in the X basis. We draw bonds between the most strongly correlated sites. In this case, that sort of nearest neighbor interactions dominate. That just forms a ring. Here it starts to group the sites in pairs, and if we keep treating those pairs as larger sites and reconnecting the most strongly correlated ones, what emerges is actually precisely a tree graph. And that was sort of what I had shown on the previous slide as kind of a discretized version of a curved space. The depth of the tree is only logarithmic in the diameter, and so this is kind of a discretized hyperbolic space. So this is kind of a first maybe toy model of seeing in the lab some emergent geometry arising as a description of the structure of correlations in the system. Now, earlier I said entanglement, and I haven't actually yet shown you anything about entanglement in this system. These are just kind of measurements of spin correlations in a single basis. And so one thing we've been exploring recently is can we actually start to measure entanglement in the system of ensembles in a cavity? So we won't do it for this tree graph so that you're not disappointed, but we're going to sort of start building up tools for characterizing entangled states here. And to do that, we'll draw on the toolbox of quantum control and quantum metrology that I touched on earlier, where one signal of entanglement is actually squeezing of quantum fluctuations. Okay, and so in our spin-1 system, these pair creation dynamics are known to give rise to squeezing of quantum fluctuations on some kind of a generalized block sphere that I've shown here, where the axes are the collective spin along the x direction and some collective quadrupole moments of the ensemble. And if you're not used to thinking about spin-1 systems, the only thing you really need to know are that we can essentially measure the average and also the fluctuations in any direction on this sphere by essentially performing microwave rotations and mapping it to an observable population difference between states. And so the first thing we can ask is, I'll show you some experiments where we work with just actually kind of an array of 4 atomic ensembles. And the first thing you can ask is if you just turn on global interactions, so no more magnetic field gradient, we're just going to turn on global interactions and ask, are the quantum fluctuations squeezed? So we do some measurement of the fluctuations as a function of orientation, and we see that actually those fluctuations dip below the so-called standard quantum limit, which is the smallest they could be in the absence of entanglement. And so that's the first way to see that in the system as a whole, we cannot write, let's say we can't write the density matrix as just a product state of the individual atoms. There's some form of entanglement. We can take this a step further and ask, is there entanglement between spatial modes in this system? So let's say I partition this into the left ensemble and the right ensemble, and I want to know whether these two are entangled. One way that you can start to assess that is by asking, how much information can measurements on subensemble B provide me about the state of ensemble A? And particularly, how much information can I gain about non-commuting observables in this subsystem A? So we can actually rely on some things we know from Heisenberg uncertainty relations. So if this were a separable state, so A and B were unentangled, then I could write down some lower bound on kind of, let's say, the uncertainty in the sum of the x's. I'm calling the two quadratures x and p to simplify notation, right? So these are just two quadratures of the collective spin. But you could write down some uncertainty relation that applies to the variance in the sum of the x's and the variance in the difference of the p's, and all that has to be larger than 2h bar if the system is unentangled. But actually, if there's entanglement in the system, so this is a good relation to write down, because if there's entanglement in the system, this relation can be violated. And the reason that's possible is that actually xa plus xb commutes with PA minus PB, right? Those two things commute, so actually these are things that in principle can be measured simultaneously, and the sum of their fluctuations can be made arbitrarily small. This was sort of eloquently named the quantum mechanics-free subsystem by Tsang and Caves, and has interesting implications for if you apply a perturbation to ensemble A that affects either quadrature, you can sort of simultaneously measure perturbations in both quadratures. Okay, so that's the concept. So this allows us to construct an entanglement witness that is essentially based on asking about fluctuations in this collective spin in two orthogonal quadratures, one of which we're looking at for the symmetric mode, ensemble A plus ensemble B, and the other orthogonal quadrature we're looking at for the anti-symmetric mode, where we look at the difference between the two ensembles. So the symmetric mode I already showed you before. There was this dip in quantum fluctuations. In this particular experiment where all we did was globally squeeze via the cavity, the anti-symmetric mode is essentially uncoupled from the cavity, and so the fluctuations there look flat. And if we sum up these two orthogonal quadratures, this entanglement witness is less than 1, which tells us there's entanglement between the two spatial modes. Okay, so we can generate sort of this global entanglement. We can show that there's entanglement between the two spatial modes. You could also ask, what if I look at one or the other mode alone? Is there entanglement just within the individual spatial modes? It turns out if I do that measurement, so just naively I just look at how squeezed is subensemble A or subensemble B, it's sort of, if you like thinking about optics, it's as if I took some squeeze state and put it on a beam splitter, and the squeezing is degraded, and actually we no longer see entanglement in the individual ensembles. But we can actually play sort of a trick here, which is we squeeze the entire system, then we locally perform a pi rotation on ensemble B, and then squeeze again. And this actually sort of undoes the entanglement between the ensembles and enhances the entanglement within the individual ensembles. And so that's something you can do if you'd like to have sort of individual entangled states of two ensembles, or potentially could also extend that to an array. Okay, right, so we have this disentangling operation that allows us to go from global entanglement to local entanglement in the system. As a brief aside, you might ask, why use the cavity at all if all you want are local correlations? And indeed, there will also be a poster from our group on a totally different approach to squeezing, which involves local Rydberg interactions. And so if you want to hear more about that, look at the poster by Jacob Hines and Gabe Moreau on Thursday. But coming back to the cavity system, what we like about this cavity system is this combination of sort of the global coupling via the cavity and also local manipulations is in principle very powerful for sort of generating programmable entanglement. So if you want to sense a global field, this sort of global entanglement is great. But if you'd rather sense a gradient in a field, you might want to sort of squeeze the difference between the two ensembles, and so there the ability to rotate 1/2 of the subsystem is useful. These independently squeezed ensembles might be useful if you want to sort of image a field and get spatial resolution. And you could also ask about sort of richer structures of entanglement where one wants to somehow program something about the graph of correlations in the system. So this would be engineering, let's say, so-called cluster states in a continuous variable sense. A minimal instance of this would be the continuous variable analog of an EPR state, which is a resource, for example, for quantum teleportation. And as one scales this up, these could be resources for computation. So what do I mean by sort of specifying a graph of correlations? So the idea here is that for this class of states known as cluster states, the structure of entanglement is specified by something known as the adjacency matrix, which essentially says that the vector of positions, so I'm calling these, again, these conjugate quadratures x and p, the vector of x's in one ensemble has some specified structure of correlations with the conjugate variables in another ensemble. So for example, in this example with two ensembles, that would say x of the left one is perfectly correlated with p of the right, perfectly in an ideal case. In practice, there'll be some finite degree of squeezing we can achieve. Or you could imagine this square cluster state, which has this richer structure of correlations. And it turns out there's actually a very general recipe in our system for preparing a state given this adjacency matrix, which is that you actually diagonalize the matrix, and its eigenvectors will tell us which collective modes to squeeze, and the eigenvalues will tell us the orientation of the squeezed quadrature. In particular, the eigenvalue is the tangent of the angle along which the noise is minimized. So for example, we can apply that to this state of two ensembles, this EPR state. And so what we should do, based on that prescription, is we should essentially first globally squeeze. That squeezes the symmetric mode, which is one of the eigenvectors. Then we can, in order to let the cavity couple to the antisymmetric mode, we'll do a local pi rotation to half of the system. We'll also do a phase space rotation that will allow us to now squeeze for the antisymmetric mode the opposite quadrature. And when we do that, we can measure sort of fluctuations in either the symmetric mode in red or the antisymmetric mode in blue, and see that they're squeezed at orientations that are 90 degrees apart, which is precisely what we were looking for to construct this EPR state. And one of the kind of neat features of this state is it means that actually ensemble B can be used to predict either x or p in ensemble A to better than the standard quantum limit. This is a condition known as steering, which is even stronger than entanglement. We're starting to look for this, and the criterion is that essentially one criterion is that the product of uncertainties in these two quadratures times 4 is less than 1. And at sort of the 1 sigma level, you see that based on this simplest condition, and if you want to hear more about sort of more sophisticated characterization of the entanglement and steering, and also very recent progress towards the 4-mode cluster state, then I'll refer you to a poster on Wednesday by Philipp Kunkel showing also even kind of the latest data from this past week. So with that, I'll just kind of summarize and say that we have been exploring first kind of exotic geometries generated by programmable interactions in this cavity QED system. The pair creation physics is a way of minimizing energy that could have interesting implications for optimization. And we're probing entanglement in the form of spin-nematic squeezing with really versatile control over the spatial structure by the combination of global cavity-mediated interactions and local control. With that, I think I'm probably out of time, so I've touched on prospects along the way. I'll just thank the team of people who've been working on these experiments, particularly Eric Cooper, Avigdor Perewell, and Philipp Kunkel are the folks behind the cavity experiment, and also I want to mention Jacob Hines and Gabriel Moreau are here with a poster on Rydberg physics, and with that, I will conclude.
Great, thank you very much. So for questions, we're running a slightly different system from the morning session. We've got some runners who are going to go up and down the aisles with microphones. So do we have a question from Bill here? Okay. Yep, please.
So I want to ask about when you put on the gradient magnetic field and shut off the correlations that were non-local. Now, at that point, you mentioned later the quadratic Zeeman effect, but does that have anything to do with the quadratic Zeeman effect?
Yeah, that's a great question. So there's an important sort of hierarchy of energy scales where the quadratic Zeeman effect in everything I showed is kind of small compared to the gradient between adjacent sites and doesn't play a role in that programming of interactions. You can play neat tricks where the quadratic Zeeman effect is strong, and that can, for example, break the symmetry between left and right in this pair creation physics. So, yeah.
Right, okay, but that wasn't part of what you showed.
But that wasn't part of what we showed.
So then shutting off the non-local correlations, does that mean that, like, if you started with a pair of m equals zeros, you couldn't get a pair that had m equals 1 in one site and m equals minus 1 in another site, but you could still get m equals plus and minus 1 in some distant site, but it had to be the same site? Is that?
Yeah, so when we shut off the sort of non-local part, what that means is that essentially to create an atom in m equals plus 1 on a particular site, I also need to create a minus 1 atom on the same site.
On that site?
Yeah, I
but
also
not
could...
the same site that the original m equals 0 was on.
So I need two m equals 0 atoms on the same site, and which can get converted to plus and minus 1.
Right, on the same site, and then that could be converted to plus and minus m on, could be another site or could be the same site. Is that right?
But the atoms aren't moving, right?
Right,
so
sure,
all that can happen is I take two atoms that are on the same site and convert those to different states on the same site, which in this case would be plus and minus 1.
The light was allowing you non-local.
And the light, so this is when I shut off the non-local part with a magnetic field gradient. Once I now modulate the light, I can turn back on processes where two atoms on different sites get converted into plus and minus 1. Yeah, great. Mm-hmm.
Thank you, and I think there was a question over there.
Yeah, over there. Can you just go through again the entanglement procedure at the beginning with the Raman scheme? It went a bit too fast.
So just the general scheme of interactions in the cavity? Yes, let's see. That is quickest to get to by, let's see. Okay, so that is here. I think this is what you meant. Is that right? So.
Yes.
Yeah, so what we're doing is essentially so we have a Raman process involving one photon from a drive field and then emission into the cavity, which allows you, if this were resonant, you could flip a spin and put a photon in the cavity. This process is off-resonant, but you still have sort of this virtual process where you flip a spin, put a photon in the cavity, and another atom can absorb that photon in sort of the reverse version of this Raman process, and that generates these kind of cavity-mediated spin exchange interactions. Did that answer the question?
Yeah, but then why do you have 3 states. Like, how does it work with the third state?
Sorry. So this is an excited state. So I gave a cartoon picture
yeah,
earlier where we had 2-level atoms, but sorry. So this is still assuming just 2 ground states, and then the additional wrinkle is actually we have our spin 1 ground state, so there would be 3 of these red states. Does that?
Yeah, that was
the question. Yeah.
The question. Like,
Yeah, and so this says generally m and m+1, and that could be -1 and 0, or 0 and 1.
because the photon that is emitted in the cavity, it cannot drive the correct transition on the other atom that is receiving it, right?
So in combination with the drive field, I can essentially have this process go backwards. So once there's a photon in the cavity, right, another atom can absorb that photon and re-emit into the drive, and that is what allows me to get these pairwise interactions.
Okay, no, it goes into right. Okay.
Maciek? Yeah,
okay, I think actually we got the microphone waiting right here. Well, just give us 1 second. We got a.
There's someone here. Okay, yeah.
Sorry, I have a question. Maybe first question is very relevant to the first question. So I just wonder, because you apply the magnetic gradient in order to have this tunable range interactions, right? With this, you will have this second-order Zeeman effect. Will this cause some inhomogeneity on the interaction strings? Depends on where the atoms are.
So again, there's sort of a hierarchy of energy scales to ensure that the quadratic Zeeman effect is small compared to the difference in Zeeman splittings between adjacent sites. And that essentially allows us to have that not be a significant effect in the graph of interactions.
Another question is also relevant to this slide. I'm just wondering, in your Hamiltonian, do you need to consider some kind of like self-interaction? What I mean is like the atom flips spin and emits a photon into the cavity, but the cavity photon gets reabsorbed by that exactly the same atom.
Yes, so in principle, the photon can also be absorbed by exactly the same atom. Again, because we're working with many atoms, that's sort of a small effect in the system as a whole, but in either case, one can sort of write down the overall Hamiltonian as basically, if I write some collective spin that I call S, it's essentially I have an S plus S minus type of an interaction, and that also does include a self interaction term. Yeah.
Thank you.
Great.
Yeah.
And maybe the last question, Maciek.
Okay, so as far as I understood, but maybe jet lag doesn't allow me to understand everything. Most of your results are based on spin squeezing inequalities, which can infer about entanglement or even steering. But there are also this type of inequalities which involve only mean values of the components of the spin and fluctuations that infer about Bell correlations. So non-locality, of course, non-locality in a sense that you close the loops, but the Bell correlations. Did you try that? Basel group has used it in first experiments.
Yeah, that's actually not something that we have looked at yet, but perhaps we should.
Maybe we should
talk
about it.
Yeah, so it would be great to chat about that. Yeah.
Great.
Yeah, thanks for the comment.
Thank you very much, Monika. Let's thank Monika again.